Why are quantum bits so fragile? Have you ever wondered why quantum bits, also known as qubits, are so delicate? This is an intriguing question that gets to the heart of quantum technology. Let's break it down in simple terms. Qubits are the building blocks of quantum computers, and they operate in a way that is quite different from regular bits found in classical computers. While a classical bit can be either a 0 or a 1, a qubit can exist in a state of superposition, meaning it can be both 0 and 1 at the same time. This unique property is what gives quantum computers their potential power. However, this also makes qubits very sensitive to their surroundings. One major reason for this fragility is a phenomenon called quantum decoherence. This occurs when qubits interact with their environment, which can include thermal fluctuations, electromagnetic radiation, or even tiny vibrations. These interactions can cause the qubit to lose its special quantum properties and behave more like a classical bit. When this happens, the information stored in the qubit starts to degrade, leading to errors in calculations. There are two main types of errors that qubits can experience. The first is a bit flip, where the state of the qubit unexpectedly changes from 0 to 1 or vice versa. The second is a phase flip, which alters the relative phase between quantum states. Both types of errors disrupt the coherence of the qubit, making it difficult to maintain accurate computations. To address these challenges, quantum computers often requiring many physical qubits to representing a single logical qubit. This is done using error correction codes. However, this can create a large overhead because error correction is only effective if the error rate of each physical qubit is below a certain threshold. If qubits are too prone to errors, adding more qubits can actually lead to more errors instead of fewer. Researchers are actively working on ways to make qubits more stable. For instance, superconducting qubits use microwave oscillators to define their states. This design makes them less susceptible to bit flip errors, similar to how a child swinging strongly in one direction is harder to push in the opposite direction. Despite these advancements, the fragility of qubits remains a significant hurdle in the development of quantum computers. Improving coherence times and reducing error rates through better materials and isolation techniques is essential. This progress is vital for creating practical quantum devices that can outperform traditional supercomputers. In practical terms, the fragility of qubits limits how long quantum computations can run reliably. It also restricts the complexity of algorithms that can be executed before errors take over. Addressing the fragility of qubits is therefore central to advancing quantum technology, which holds promise for future applications in communication, simulation, and computing.